Good morning, everyone. My name is Ferron. I'm an associate professor at the University of Texas at Austin. I know on the program it says Andre Fuqua. That is one of my graduate students. And what I'm going to present to you today is work that he is doing in pursuit of his dissertation. And I do thank you all for being here at 8 a.m. If I wasn't the first speaker, I don't know if I would be here at 8 a.m., but I am. Okay. So today I'm going to talk to you about potential for use of earthen materials in 3D printing applications. Since the beginning of time, humans have been building with earth, and it makes sense because when we look around us, earth is, around us and it's available everywhere, which is one of the benefits of building with earth. And over here, I show some examples of some earthen structures. We can see the Great Wall of China, in which some of the watchtowers and fortifications were made using earth. We have the Great Mosque over here, which is actually considered to be like one of the greatest examples of earthen architecture in the world. And this was made primarily with earth. And then we have Tayas Pueblo, which is a community in New Mexico. And this also was made entirely with earthen materials. And what's really cool about these structures is that, considering their long age, they are all still around and still presently in use. Particularly with respect to Taos Pueblo, it's considered to be one of the longest continuous use for humans in North America, right? So that's showing you the testament to the resiliency and strength of earthen materials, which we tend not to really think about as being, strong and resilient. And when we look at earthen materials, it's actually used everywhere. Just about every continent will have some type of earthen architecture. So over here, this is showing you a map of where there's regions in which there's earthen architecture. You can see it's pretty well distributed. In addition, earthen architecture is not just used in warm climates, as some people may think, right? Over here, we can see this multifamily building that was built in 1955 in Germany. When we look at earthen materials, there's many different ways that you can build an earthen building. Perhaps the one that most people are familiar with is adobe. Adobe is the type of earthen construction when you take soil, typically you'll mix it with some sand too. You'll have it in like a mold and just hand mold it. Then we have cob, which is another type of earthen material in which you have your earth, you have your sand, and you also mix it with some straw. And then you have rammed earth, which is a type of earthen construction in which you have your forms built to a certain height, and then you will have your soil put inside of it and you'll tamp it down, and then you put another form on top of it, and then you fill it with soil and then you tamp it down. And a lot of architects like the look of rammed earth because you could add pigments to it and then change the color of each layer. So you can have some really nice features with it. And over here, this is just showing you some examples of each one of these construction earthen materials. However, over the last, I'm going to say, decade or so, there's been this, renewed interest in looking at earthen materials. A lot of this has been driven for looking at trying to have economical, affordable materials with respect to housing development to address concerns with respect to housing scarcity. But in addition, there's a big motivation with respect to looking at how we can try to mitigate some of the effects that the building and construction industry is having with respect to climate change. And when we look at earthen materials, we see that they have a much lower embodied energy and carbon footprint than our beloved concrete. So over here, this is showing you an example of rammed earth, which is one of the methods that I talked about before. And compared to concrete, we can see that rammed earth is going to be a fraction of the carbon footprint and embodied energy of concrete material. So this is a strong motivator in which you're seeing a lot of, I would say, people who are really focused on sustainability is looking at having alternative materials to design their house. This renewed interest in earthen construction has also led to a renewed interest in ways that we can manufacture earthen materials. So over here, this is showing you two examples. One is compressed earthen blocks. Oops, that should be. Take off the sound. Over here, this is showing you a video of compressed earthen block masonry. And the way you can think about this is like an extruded type, a free-form extruded type of earthen construction. The soil is coming in, it gets compressed when it went down, and then it's extruded out, right? And you can see when he picks it up, it's going to have it's going to have shape stability, it's well formed. In some applications, people are building directly with it, but in many cases, you will actually cure it too. So this is Jim Halleck over here. That guy, he's a big earthing contractor in the United States. And over here, this is showing an example of 3D printing with earthen materials. This is from Ron. He's an architect and also a professor at the University of California. And he's been doing a lot of work really looking at using earthen materials from like the architecture perspective. However, when we look at Earth is, unique and different than concrete, and there's unique challenges that are present with dealing with Earth. One of the first challenge that you have with Earth is moisture resistance, right? We all know that when you have Earth and you mix it with water, you're going to have muddy puddles, right? And nobody wants a home that is going to be a muddy puddle. But the great thing about this is that we have ways to address this. And this is where our beloved cement comes into place. With earthen materials, in order to increase its strength, in order to increase its water resistance, you will need to stabilize it. And in fact, if you want to use it for exterior use, you need to have a chemical stabilizer. The most common type of chemical stabilizer that is used is Portland cement. You do have other types of stabilizers such as lime and metakaolin and other forms, but cement is the one that you'll see typically used in the field. Around 3 to 10% of the content of your soil would be cement. And similar to what would happen in soil cement, which is a committee here at ACI, when you add your cement to your soil, you're going to, and you allow it to cure, you're going to have that hydration reaction that's going to form the precipitation of CSH. The CSH is then going to bond to the soil particles, so that's going to fill the voids as well as to increase the strength. So this is where chemical stabilization comes into play. Another challenge that people have with respect to earthen materials is safety. And with respect to fire resistance, there's been a lot of studies that have shown that fire resistance is perhaps not even a big concern with earthen materials. And it makes sense because when you heat earth, you're actually making it to be stronger. You can think about like potteries and clays when you heat it up, right? So earthen materials actually have really, really, really good fire resistance. Structural integrity is a place where there's a lot of work going on from the structure side. And what has been found is that similar to the way that you can add chemical stabilizers to increase the water resistance, you can add reinforcement to it. So there's various types of fibers that you can add to your earthen masonry in order to increase the strength. There's geosynthetics materials that has been added to increase the strength. So there's a lot of work going on in this space. And there's one state that I'm aware of that explicitly addresses earthen materials in a building code, and that is New Mexico, which makes sense because remember that first slide when I showed you, Cayos Pueblo, they do a lot of earthen construction there. And with respect to specifying the material, the information that they have is that the soil must have a strength of around 300 psi. So very similar to like thinking about like masonry type of construction, and must have a modulus of rupture of around 50 psi. This is basically it with respect to material properties. Well, there's one more. It states for stabilization, you need to have 6% cement. But there's no information about shrinkage. There's nothing in there about like plasticity limits or anything like that. It's just strength. This is your qualifier with respect to having this material. Another challenge that we have is communication differences. So I remember when I went to college, I went to Howard University in Washington, D.C. I'm from New York. We say soda. I started meeting people from the Midwest, and all of a sudden it was pop. And I'm like, wait, what? Right? So it's this big debate over soda and pop. Right now in my household, we're having a debate over is it book bag or backpack. I say book bag. My kids say backpack, right? Same thing, right? But different terms for describing something. And that's actually what's happening right now in the earthen space. When you talk to contractors in this area, they have a lot of methods that they use to try to identify soils, but the methods that they have are really empirical based. This test is a jar test. It's actually pretty cool. You put the soil inside, you add a water, you add a dispersant, and then over time you'll see that the different fractions are going to separate. They use this as a way to try to identify suitable soils with respect to clay content, but it's not like it's and it's just like, okay, we have a lot of clay, then this is good. It's not like it's a percentage or anything. There's a shrink box test that I know one contractor is using as a way to try to identify suitable soils. Again, there's really no guidance there with respect to, what is good or what is bad. There's a cigar test, which is trying to look at plasticity. This is a thumb over here. You essentially take the soil, you roll it in your hand, and you're looking to see at what point it's going to crack. And then there's other tests. The ball test is really used a lot in the field. This is to identify whether you have the right moisture content. So you take your soil, you would have added water to it, you squeeze it, and then you drop it on the floor. And depending on how it splatters, they're like, okay, this is good, this is bad. And then there's even a sniff test. The sniff test is used in order to identify soils with respect to organic matter, right? So these will be some of the languages, the terms, the testing that you will see contractors using in the earth and building space. And then when we think about engineers, if you're a civil engineer, you're used to geotechnical engineering tests. We're talking about Atterberg limits. We're talking about particle size distribution. We're trying to get to the same thing. We're trying to look at, how much clays do you have? What's the particle size of it? But it's a completely different language. And furthermore, even if we had all this information as engineers, we don't really know what to do with it. So a big challenge that we have is this link between the engineering properties and the performance that we need for earthen materials for building application. But this challenge presents an opportunity. And this opportunity is really looking at engineering earthen mix for buildings application. One of the ways to do this is to have a good understanding of the role of moisture content of earthen materials. I talked about moisture resistance, but in order to make these earthen materials, you have to have some moisture in it too. When we look at rammed earth, you have around 5% moisture. Of course, it depends on the soil type. When you look at cob, it's around 10%. When we look at adobe, it's around 15%. Compressed earth and adobe actually have similar moisture contents. And then when we look at 3D printing, you're going from anywhere from like 20 to maybe 30%, right? In order to gain the consistency that you need. And what we want to do at UT Austin is really look at engineering this earthen mix. So the same way that we have engineered mixes for concrete construction, the same way that we have like engineered mix for soil cement for foundation applications, we really want to look at trying to engineer this mix for building applications. So what we're doing in our lab is we're gaining soils from various contractors in Texas. We're characterizing the soils. We're varying the moisture content, doing our typical geotechnical engineering tests, and we're adding different stabilizers at different stabilizer contents. And then our goal is to determine the density. There's different ways to determine density. There's a static density, static compaction test. There's a dynamic compaction test. We're going to be looking at both of those type of compaction tests because we're not sure yet which one is best representative for building construction applications. In addition, instead of doing like the ball test or anything like that, we really want to look at having a quantitative test to characterize the consistency of these mixtures. So we're going to be looking at the fresh state properties and trying to tie it to rheological parameters. And then we're going to be looking at this for these two modern type of earthen materials. So the compressed earthen block construction as well as the 3D printed material. We're doing various types of characterization tests from strength to moisture resistance, looking at porosity and permeability. We've got some really interesting work looking at indoor air quality. One of the benefits of earth that is different than concrete is the fact that it's considered to be a breathing material, a living material. So I was really interested in whether we can use earthen materials as passive removal agents for some toxins in the environment. And what we're finding is that it's doing a really good job of removing siloxanes, which is basically a VOC that's emitted from human health products. So we're also looking at indoor air quality and how you can use earthen materials to remove toxins in the environment. And then our real goal here is to link these various performance with the density and rheology so we can come up with parameters for when you have a good performing material. So in conclusion, we see that there's the renewed interest for earthen materials, and we know that earthen materials are used all over the world around 40% of humans are living in earthen, live or work in an earthen building around the world. And we know that in order to really advance this field, that you're going to have chemical stabilization. You need it when you're looking at, exterior applications of earthen masonry. And truly looking at engineering of the mixture, understanding how to identify suitable soils and understanding how mixture design is going to impact the properties is a opportunity in this area to advance the use of these materials. So it's no longer just an art, but more so an engineering practice. And with that, I would like to say thank you. This is my student Andre, who's been doing this work. This picture has nothing to do with this presentation, but I love it. This is a picture of some concrete blocks. We have a big outdoor exposure yard at UT Austin. And right now, this is the season in which the blue bonnets are blooming in Texas. So it looks really beautiful if you were to come to our lab. Thank you.